as analytic functions. All right. So we already talked about the half plane of absolute convergence and the half plane of ordinary convergence, and we noticed that the gap between those two in terms of the line is no more than 1, and we gave an example where it is exactly 1. And then in the half plane of absolute convergence, from multiplicative functions, we wrote down the Euler products, and I wrote some familiar Euler products for thin functions like the Euler function, the divisor function, and so on and so forth. Okay, so now we're going to look at analytic function, Dirichlet series as analytic functions. So I'm going to recall a well-known theorem from complex variables. So this is a known theorem. So let Fn of z be a sequence of analytic functions, analytic in the domain D. Domain is one connected set. And let Fn of z converge to F of z uniformly on compact subsets of D. That means all compact subsets of D. Then F of z is analytic D. So a uniformly convergent sequence of analytic functions, the limit will be analytic. So this is coming from uniform convergence. Okay. So I just give a one-line, the various ways in which one can prove this. A one-line proof of this is, for each point W in this domain, draw a circle, if you want, C around W with C contained in D. Okay. Then your F of W, Fn of W, sorry, is 1 over 2 pi I integral over this circle F of Z dz divided by Z minus W, right, by the Cauchy formula. Fn. And the circle is compact, and so the limit of this will be the limit, but I can now interchange the integral and the limit, and then we will get F of W. Okay. Then F of W, which is the limit as n tends to infinity of Fn of W, will be the integral of this limit that's equal to that's an analytic function which renders F the analytic. Very good. So what that means is, analytic means it is, the definition of analytic is that it is differentiable at every point. Right? So that's the definition of analytic. Consequently, your F prime of W, again, you can do this through the limit, will be 1 over 2 pi I of the counter integral of F of Z dz So that's the formula for the derivative. I mean, you apply this formula for each fn, and then you can take the limit if you want. But you can also use this. All right. So this is the reason why the uniform limit of analytic functions is analytic. Now, of course, in this case, we are using the Cauchy integral formula. In the real variable calculus, also you can establish the limit is differentiable, but then you won't have a Cauchy integral formula. You actually have to do it using epsilons and deltas and show that the limit function, the limit will be continuous, the limit will be differentiable, all in a uniform convergence. Okay, so we have that. Now let us apply this to Dirichlet series. So our theorem is, so that's just a theorem without a number. So this is our first theorem for today. The theorem is, let f of s be summation, if we want, f of n over n to the s, have half plane, we have half plane of convergence sigma greater than sigma c. So that's your abscissa of convergence. Then, in that half plane, f of s is an analytic function of s. So every Dirichlet series is automatically an analytic function in the half plane of convergence. You don't even need absolute convergence for this. Absolute convergence is used for rearrangements. So if you're multiplying the Dirichlet series and you want to rearrange and get the coefficients using the Dirichlet convolution, then you need absolute convergence. But you want to do point term by term differentiation, you can do that in the half plane of convergence itself. You don't need the half plane of absolute convergence. Okay, so proof. So the proof is going to use the fact that the Dirichlet series will converge uniformly to the limit in compact subsets of the half plane. So that's really what we are going to be. Once we have that, if it converges uniformly, each term of the Dirichlet series, f of n over n to the s, represents an analytic function. So since the infinite series, take now the sequence of partial sums, that's an analytic function. That sequence of partial sums is now converging uniformly, so the limit will be an analytic function. So it just comes from this theorem. Okay, so all we need to show is that the Dirichlet series converges uniformly in all compact subsets you call the subsets T of the half plane. All right, so draw a picture. So this is, let's say, sigma c, and I have some compact subset here. So I want to show uniform convergence in this compact subset. So what we do is this. You take a point S0 with sigma naught greater than sigma c, but the sigma naught is strictly less than the minimum of all sigmas as s ranges through t. Right? So s ranges through t. Take the leftmost point, and s naught is to the left. Any s naught will work. So choose an s naught in the half plane, in the open half plane, but to the right. Okay. Now, so we know that the Dirichlet series converges in the half plane in the line. Sigma equal to sigma naught. So it's convergent everywhere here. All right, so now we have an estimate, right? Recall an estimate that we established before. So, pick any S in the half plane so pick any S which is to the right of this. We have an estimate. We know that. I forget the numbering of this lemma, that if I sum f of n over n to the s between A and B, okay, this is the Cauchy estimate for the remainder of the series. This is less than or equal to, so it converges on the line, and so its partial sums are bounded by some m. That m is what I'm going to use here. So that's the bound of the partial sum. Then this is less than or equal to, just want to quote this bound correctly, 2m over a to the power sigma minus sigma naught times 1 plus absolute value of s minus s naught divided by sigma minus sigma naught. We established this before. Okay, so what does this mean? This is going to 0 uniformly because the smallest value of this will be at the leftmost point. But the leftmost point is removed from S naught because of the compactness. Therefore, this is going to 0, at least at the rate where I replace sigma by the leftmost position, whatever sigma I get in the leftmost position. And now I can let A tend to infinity. It doesn't matter what B is. It doesn't matter what sigma is. It is A to a positive power. This is bounded. So as long as I can bound this, this will converge uniformly to 0. So clearly, the right-hand side, 1, tends to 0 uniformly for S belonging to T, if provided we can bound the expression, the term, only if we bound that, 1 plus S minus S naught over sigma minus sigma naught. I have to bound this. But what is this? S minus S naught is the distance of S from here. Sigma minus sigma naught is the difference in the real parts. So this quantity is actually uniformly bounded as long as I am within a sector. Because if I choose S minus S naught is like that hypotenuse, sigma minus sigma naught is the base, right? S could even be outside this. It could be inside or outside. So S minus S naught over sigma minus sigma naught is the cosecant of that angle. So as long as I keep the cosecant of that angle bounded, this is bounded. I'm sorry, as long, yeah. So the cosecant must be bounded, which means that angle should not have the entire opening. I mean, as long as it is some number less than pi over 2, we are done. Okay, so now we say the quantity in 2 is bounded as long as S belongs to a sector located, or the S belongs to the interior of the sector. The interior could also mean boundary, okay? Interior boundary of a sector located at S0 with opening less than pi. So you see what I'm saying? Both sides make it symmetric. And so it's uniformly bounded in such a sector. But I can make this arbitrary. So as long as I'm given this object, this S0 could be anywhere. It doesn't have, this S0 could be far away. I can still choose a sector inside which this will lie. It doesn't matter where the S0 is located on the line. The farther away S0 is, the wider the opening of the sector, but you can still get this sector to open less than 180 degrees. And that's all is needed. Okay. And given S0 and T, a suitable sector can be found. Such that T lies inside that sector. So this uniform convergence is really in that sector opening. As long as it is less than pi, we have uniform convergence. But that's arbitrary, so it's uniformly convergent. So that shows analyticity in that sector, but the sector is arbitrary, so it's analytic in the entire half plane. So that's what, so we have established that every Dirichlet series is an analytic function in the half plane. By the way, the converse is not true, meaning just because you give me an analytic function in a half plane doesn't mean you can represent it by a Dirichlet series. Because a Dirichlet series representation has some special properties. If you have a Dirichlet series representation, then as I approach infinity, I will go uniformly to f of 1. It depends only on the real part. It doesn't depend upon the imaginary part. Okay, that only tells you something about f of 1. What about f of 2? Well, you have to subtract f of 1. So assume that property holds. That's a necessary condition. Now I have to subtract f of 1. And now f of 2 will be obtained by thinking of 2 to the power 1 over 2 to the power of s as dominating over 1 over 3 to the power of s and so on. So you subtract that difference, multiply by 2 to the power of s and go to the limit, and that limit then must converge uniformly as sigma goes to infinity, and whatever that limit is, that's your f of 2. Then after that you subtract the first two terms, and then you do this, and so you can write down an infinite sequence of conditions which all satisfied will guarantee that this has a Dirichlet series representation, but that's far too complicated. But what is nice about power series is every power series represents, convergent power series represents an analytic function. And conversely, every analytic function admits a power series representation around that point. So this is so nice, it's an if and only if. That's why there is this wonderful theory of power series, which is functions of a complex variable, right? Because we were able to characterize analytic functions in terms of power series. Now, I don't know, you guys are TAs for calculus classes, but this is something I hope that you will emphasize it as TAs. I mean, you can have a function of a real variable which is differentiable everywhere to arbitrary degrees, but at the same time, differentiability does not imply the existence of a power series within a certain thing. So one example I usually give is like 1 over 1 plus x squared, which is differentiable all the way through, but if you take the power series representation around the origin, the power series is only for radius 1. And even though the function is differentiable everywhere as many times as you like, but this sort of thing doesn't happen in complex variables. The radius of convergence of the power series tells you the radial validity from that point anyway. So it tells you what is going on more precisely. So, so even though we have a general theory of Dirichlet series, which combines Dirichlet series, classical Dirichlet series on one hand and power series on the other, we have to pay attention to the fact that power series have some special properties that other Dirichlet series do not have. In fact, we are now going to prove a theorem where we will fall back on power series to help us. Okay, but before we do that, let us note the following. So, theorem 2 is that f of s be summation f of n over n to the s, n from 1 to infinity, in sigma greater than sigma c. Then f prime of s is summation f of n log n over n to the s from 1 to infinity. Of course, n equal to 1 doesn't exist because of the log. I'm just writing it that way. And this, all I did was to do term by term differentiation. The derivative of f of n over n to the s is f of n times the derivative of 1 over n to the s, e to the minus s log n. I got the log n out. And more generally, the kth derivative of s minus 1 to the k summation f of n log n to the power of k divided by n to the s. Okay? We're going to be using this formula now. So we can differentiate term by term. Already we have encountered one case where we differentiated term by term, and that was zeta of s and zeta prime of s that we used, but this is in general. All right, so now we're going to focus on Dirichlet series with non-negative coefficients. We're going to prove the famous theorem of Landau. When I say non-negative coefficients, I mean for sufficiently large. So we are now saying that a of n is greater than or equal to 0 for all n greater than or equal to n naught, or f of n greater than or equal to 0 for n greater than or equal to n naught. So from some point on. So first observation is when you have Dirichlet series with non-negative coefficients, the abscissa of convergence and the abscissa of absolute convergence are the same, so we don't have to worry about that. Now let us state a theorem, Landau's theorem. So this is theorem 3. This is Landau. I want you to understand exactly what is being asserted in this theorem. Okay? So, let f of s be equal to summation, some Dirichlet series, in sigma greater than some c. This need not necessarily be the abscissa of convergence. Suppose you have a function represented as a Dirichlet series in this, thereby rendering it an analytic function. All right? This is still an open half plane. All right? Let an be greater than or equal to 0 for all n greater than or equal to n naught. So I'm now dealing with a Dirichlet series with non-negative coefficients. Suppose, now here's the important assumption. Suppose f of s is analytic at c. We're not yet saying that it has got a Dirichlet series representation. At the point c, it turns out that this f of s can be made into an analytic function by some process. That means it's analytic in a disk around the point c. Then the claim is there exists epsilon greater than 0 such that the Dirichlet series representation of f of s holds in sigma c minus epsilon. Then there exists epsilon greater than 0 such that f of s equal to summation an for f to the s for sigma greater than C minus epsilon. You can actually move the line of convergence to the left by a certain amount. So what does that mean? That means if that C was actually equal to sigma C, which is the abscissa of convergence, which means you cannot move further to the left. If you're having a Dirichlet series with non-negative coefficients and you're actually sitting on the line of abscissa of convergence, then that point C, sigma C on the real axis, will be a point of non-analyticity for the function. Because if it were a point of analyticity, this theorem tells you I can shift the line a little bit to the left. So that's an obstacle for analytic continuation. That point will be a point of non-analyticity. All right. Consequently, if a n greater or equal to 0 for all n greater than n naught, sigma c f of s is not analytic at the point sigma c on the real line. At that point, it cannot be analytic, because if it were analytic at that point, sigma c, then that means it's analytic in a region around it. Then I can shift this by what I've said here to the left. But then this ceases to be the abscissa of convergence. So let us prove this. But to prove this, we're going to fall back on power series. So power series cannot be ignored. Okay, power series are not special. Even though they're part of the theory of generalized Dirichlet series, they occupy a very special place. So let us prove this theorem of Landau, then I will give you some history behind this. Proof. Okay. All right, so we're proving this theorem. This is a consequence. We only need to prove this. All right, so in this picture, I'm going to draw another picture. I'm going to put a C here. So that's the C. I first will take a point to the right of C. You can take any point to the right of C for this proof to work, but since we don't want to be worried about fractions and so on, I'll take a point 1 unit to the right. But any point to the right will work. All right, consider A, which is 1 plus C. Now, so drawing this picture, this is C, and this is 1 plus C. The function is analytic at C, so that means there is a small disk around C where this function is analytic. That means the function is analytic in this half plane over that kink and down. But this radius is something, it's not arbitrarily small. There is some definite radius, however small it is, around which that circle this function is analytic, which means starting from this A, definitely the function is analytic in a circle of radius 1. But because of this, I can extend that a little bit beyond and still get a circle which, like an eyeball, can be squeezed and can still be inside that other circle. Right? I mean, I can't draw my picture. I'm not so very good with pictures, but you see what is going on. I mean, this is a circle of some small radius, so I can definitely go up to 1, but I can go a little bit beyond and still squeeze a circle which is inside here. Okay, so consider A equal to 1 plus C. Since F is no Dirichlet series yet, it's only analytic. We're talking about analytic. Since F is analytic at C, there exists some radius R such that F is analytic in absolute Z minus C less than R. Okay. This means there exists epsilon greater than 0 dependent on R. So this R is going to determine that epsilon such that f of s is analytic, I should say s minus c, right? S is the value. So there exists an epsilon greater than 0 dependent on R such that f of s is analytic in absolute value of s minus a less than, in fact I can put less than or equal to 1 plus epsilon. I can just dig in a little bit into that. That's the epsilon with which I'm going to work. Now I use the fact that if a function is analytic in a circle, it can be expanded as a power series in that circle. Okay? See, this kind of fact I can't talk about Dirichlet series. Just because a function is analytic doesn't mean it has a Dirichlet series representation. It always has a power series representation in whatever circle in which it is analytic. All right. Thus, we may write f of s as a power series. K equal to 0 to infinity. I can put s minus a to the power of k over k factorial. And what are the coefficients? The coefficients are the kth derivative at the point A. Right? This is the standard power series representation. We may write this, and this is true for absolute value of s minus a less than or equal to 1 plus epsilon. Actually, what I mean is, I can do 1 plus epsilon boundary because I can go a little bit beyond that and still get an open disk. That's what it means. So you accept this. But what is fk of a? I need to know the value of fk of a. But a is lying in the half plane of convergence. And in the half plane of convergence, we notice that I can differentiate the Dirichlet series term by term. So I have a formula for fk of a, but only for the a sitting inside the half plane of convergence. Okay. All right. Since a lies in the half plane of convergence, we know that, just use that formula. Fk, the kth derivative at the point A, is summation n from 1 to infinity minus 1 to the k f of n is now a n log n to the k